How's it going, ladies and gentlemen? Mr. Johnny here again with some 11.5 vapor pressure problems. All right, so you got to remember vapor pressure is it's kind of self-explanatory. It's the pressure caused by the vapor of a liquid. So if we had a sealed container, let's say with some water in it, all right, well, that water is some of it's going to evaporate into vapor, and that vapor is going to cause a pressure on the container, and that's all vapor pressure is. All right, so this first question is kind of a definition question. It says, what the vapor pressure of any substance at its normal boiling point is blank. And normal boiling point is defined as the vapor, the temperature at which the vapor pressure of a liquid is 1 atmosphere. All right, so normal means we're at 1 atmosphere. And if it's boiling, that boiling is when the vapor pressure equals the environmental pressure, so the pressure of the environment, right? So if we're talking about normal conditions, we're talking about 1 atmosphere. Its boiling point is going to be when its vapor pressure is 1 atmosphere. 19, of the following, blank is the least volatile. So you got to remember volatile means, its tendency to go into the gas phase. So the least volatile would be the least likely to go into the gas phase. Well, what's going to determine that? It's going to be attractive forces. So we're going to look for the one that has the strongest attractive forces, because those molecules are going to be held together more tightly or strongly and less likely to go into the gas phase. All right, well, if you take a look, again, all these choices are nonpolar, we've seen problems like this before. So that means they all have London dispersion as their primary attractive force. So what do we know about London dispersion? Well, as the mass goes up, the attractive force goes up. So if it's asking for the least volatile, it's asking for the strongest London dispersion forces, which means it wants the most massive one. So if we take a look, which one of these is the most massive, it'd be choice A. It's the heaviest. 20, the vapor pressure of a liquid blank. All right, well, let's think about this. They're talking about, you probably, can recall these charts where you've seen them in regions where they look like this, and then you got another substance and it goes up like that, and you got another substance that goes up like that. Well, it all, where this is T and then this is vapor pressure, T for temp. So if you take a look, as the temperature goes up, the vapor pressure goes up. But it's not linear. Linear would mean it's like a straight line. Linear would mean, hey, it's in this, it's going this way, it's straight, but it's not. So it increases non-linearly with temperature. So the choice B. 21, using a chart. This is based on the figure above. The boiling point of diethyl ether under an external pressure of blank is blank. Or I'm sorry, under 1.32 atmospheres is blank. All right, so first step, let's find this diethyl ether. All right, it's this line right here. And it wants the boiling point at that pressure. So first we got to convert this, right? We got to go, all right, well, this vapor pressure is in torr, and they gave me atmosphere. So I got to do 1.32 atmospheres times 760 torr per atmosphere. So what do I get? I get roughly 1,000 torr, which is going to be like the very top of this line. So I'm going to go over, that's where it is. Now you got to remember that boiling point, at the boiling point, the vapor pressure equals the pressure of the environment. So we're looking for at what temperature will these things match up. So it's just kind of you hit the line, you go down, it's 40 degrees Celsius would be the boiling point. 22, same kind of problem, but looking at different stuff. This is based on the figure above. The boiling point of ethyl alcohol under external pressure of this ATM is this temperature. All right. So let's find the line we're talking about. Ethyl alcohol is this line right here, right? That second line in. Looking at that. External pressure is, again, they give it to us in atmospheres, so we got to do a quick conversion. Got to times that by 760 to torr per atmosphere. And we get 55 torr. So the pressure is really low. 55 torr, I would estimate, let's see, 200, that'd be 155, probably be right about here. So I'm going to go over till I hit that line, and I'm going to go down. All right, so hopefully there's an answer around 20. Sure enough, there is. All right, and then I think there's one more. 23, based on the figure above, the boiling point of water under an external pressure. Again, they give us the atmospheres. Convert that to torr because the chart is using torr. And you get 375 torr. So you go 375, that's about here. Let me go over till it hits water. It's about there. You can go down. That's about 80. So that's the boiling point at that pressure. What's kind of cool, a little extra information for you. So remember, you can't, like, if you're trying to heat up, if you're trying to cook something, or boil an egg, let's say, well, it can only get as hot as the boiling point, right? So if you've ever read, instructions for at altitude baking instructions, it's usually you got to cook it longer, lower temperature. That's because the water will boil off at a lower temperature. So you can't get it as hot, so it takes longer to cook. The opposite is true, too. If you've ever heard or seen pressure cookers, basically what they do is it's like a pot, right? So that's my pot with a lid that seals it completely. So you got some liquid in there and you're heating it up, and inside the pressure is getting really high, right? The pressure's going up, which means that the boiling point is going to go up, which means you can get it hotter, which means you can cook it quicker. Interesting. I don't care who you are. All right, well, I hope that helped, and I will see you in class. Bring questions.